Hello children! In the previous chapter on electricity, you have learned about the heating effects of electric current. What could be the other effects of electric current? We use many electric appliances in our daily life such as electric motors, electric generators, electric calling bells, electric cranes, etc. How do they work? How do electromagnets work? Is there any relation between electricity and magnetism? Can we produce magnetism from electricity? In this chapter, you will study about magnetic fields and electromagnetic effects. In today's session, you will learn about the Oersterd experiment and magnetic field lines from the lesson Electromagnetism of Class 10 Physics. Learning outcomes. At the end of this session, you will be able to understand about Oersterd experiment, magnetic field, magnetic field lines, magnetic flux, magnetic flux density. Keywords: Oersterd experiment, bar magnet, compass, magnetic field, the region around a magnetic material, magnetic field lines, magnetic flux, a measurement of the total magnetic field that passes through a given area. Magnetic flux density. Before starting the session, let's look at this concept map. Oersterd experiment. Take a straight thick copper wire and place it between the point X and Y in an electric circuit. The wire XY is kept perpendicular to the plane of paper. Now, place a small compass near this copper wire horizontally. See the position of its needle. Pass the current through the circuit by inserting the key into the plug. Observe the change in the position of the compass needle. We see that the needle is deflected. It means that the electric current passing through the copper wire has produced a magnetic effect. Thus, we can say that electricity and magnetism are linked to each other. This was found by Hans Christian Oersted. One of the leading scientists of the 19th century who played a crucial role in understanding electromagnetism. The unit of magnetic field strength is named the Oersterd in his honor. Magnetic field and magnetic field lines. We use the term field when a force gets applied on an object by another object without there being any physical contact between them. Let us understand the concept of magnetic field and the lines of magnetic field by conducting an activity. Fix a sheet of white paper on a drawing board using some adhesive material. Place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet. Now tap the board gently. The iron fillings arrange themselves in a pattern. The magnet exerts its influence in the region surrounding it. Therefore, the iron fillings experience a force. The force thus exerted makes iron fillings to arrange in a pattern. The region surrounding a magnet in which the force of the magnet can be detected is said to have an magnetic field. The strength of the field varies in proportion with its distance from the bar magnet. The lines along which the iron fillings align themselves represent magnetic field lines. Let us consider another activity to understand the concept of the magnetic field and the magnetic field lines. Take a small compass and a bar magnet. Place the magnet on a sheet of white paper fixed on a drawing board using some adhesive material. Mark the boundary of the magnet. Place the compass near the north pole of the magnet. The south pole of the needle points towards the north pole of the magnet. The north pole of the compass is directed away from the north pole of the magnet. Mark the position of two ends of the needle. Now move the needle to a new position such that its south pole occupies the position previously occupied by its north pole. In this way, proceed step by step till you reach the south pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents a field line. Repeat the above procedure and draw as many lines as you can. You will get a pattern. These lines represent the magnetic field around the magnet. These are known as magnetic field lines. We observe that the deflection in the compass needle increases as the needle is moved towards the poles. Magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, it is taken by convention that the field lines emerge from the North Pole and merge at the South Pole. Inside the magnet, the direction of field lines is from its South Pole to its North Pole. The magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. Observe the spacing between lines. In some places, the field lines are crowded near the poles of a bar magnet, and in some places, the field lines are spread apart at long distances from the bar magnet. From this, we can conclude that the field is strong when lines are crowded and the field is weak when lines are spaced apart. No two field lines are found to cross each other. Magnetic flux. To understand the concept of magnetic flux, let us consider a uniform magnetic field in space. Imagine a plane of a certain area A placed perpendicular to the field at a certain point in the magnetic field. You notice that a few field lines pass through this plane. This number gives an estimation of the strength of the field at that point. The number of lines passing through the plane of area A perpendicular to the field is called magnetic flux. It is denoted by phi. The SI unit of magnetic flux is Weber. Flux depends on the orientation of the plane in the field. Magnetic flux density. To understand the concept of magnetic flux density, let us consider a uniform magnetic field in space. Imagine a plane is perpendicular to the field and has unit area. Then the flux through its plane of unit area gives the strength of the field. This strength of the field is technically called magnetic flux density, B. Magnetic flux density is defined as the magnetic flux passing through a unit area taken perpendicular to the field. Let the flux through the area A be phi. Then the flux through the unit area perpendicular to the field is equal to phi by A. The ratio of magnetic flux passing through a plane perpendicular to the field and the area of the plane is called the magnetic flux density. So, magnetic flux density equals to magnetic flux by area, which means B equals to phi by A, or phi equals to B into A. Units of magnetic flux density is Weber by meter square. It is also called Tesla. Points to remember. In 1820, Oersted discovered that a compass needle gets deflected when an electric current passed through a metallic wire placed nearby. A magnetic field exists in the region surrounding a magnet, in which the force of the magnet can be detected. Magnetic field is a quantity that has both direction and magnitude. The magnetic field lines are closed curves. The number of lines passing through the plane of area A perpendicular to the field is called magnetic flux. It is denoted by phi. The SI unit of magnetic flux is Weber. The ratio of magnetic flux passing through a plane perpendicular to the field and the area of the plane is called the magnetic flux density. The unit of magnetic flux density is Weber by meter square. It is also called Tesla.